Okay, so welcome everyone to Guided Study Group Week 8 of Statistic 100. So this week we're going to be working on Lesson 8, which is understanding the uncertainty. And so in this lesson, the first thing and also the very important part is probability, also called like the chance of something happen. So we have some rules of probability. So probability is like the chance, and so it always be between 0 and 1. And so any probability that's exceed 1 or a negative are also not non-existent. And second rule is that if the outcomes cannot happen simultaneously, the probability that at least one of them occurs can be found by adding their individual probabilities. So say thing like you have like you want to find the probability of something is at least bigger than a number, then you have to add the probability of your value bigger than that number and the probability of your value equals to that number. The third rule is that the chance of something is equal to 1 minus the chance of the opposite thing. So say if you have like only one possibility and like one possible outcome and another outcome is different from that outcome. So to find the probability of the second one, you want to take 1 minus the probability of the first one. 4, if knowing how one event turns out doesn't affect the probability of a second event, then we say the events are independent. The chance that two independent events both occur is found by multiplying the chances. So like, because they're independent, you need the first one happen and then the second one happen, because it's an and not just or. That's why we have to multiply them. In the case of rule 2, is when you have it equal to or bigger than, so it's an or, so you just add them together. But if you need both of them happen at the same time and they're independent, it's an and between those two events, then it's the product of their probability. And then the last rule is that if the ways in which one event can happen are a subset of the ways that a second event happen, then the first event cannot have a higher probability. So basically, an example to say this is like, if you need a number to be at least some value, so the chance, the events that your values is equal to that value or your value is bigger than that value is just one possibility in the at least statement. So the at least statement means that you have two possibilities. Either your value equals to that given one or your value is bigger than that. So either the probability of these two small events cannot be higher than the probability of the at least statement because it includes both of the possible outcomes. Then we have the concept of expectations and expected value. So expected value is just basically kind of like an average value of measurement. So what is, given the probability of all these possible outcomes, what is going to be your expected outcome? And so to find that, we take the sum over the possible values, multiply the probability of getting that value. So say if you have 3 outcomes, which is A, B, and C, and the probability of each is like 0.1, 0.3, and then 0.6, note that the probability has to sum up to 1. Then your expected value is going to be, it's going to be 0.1A plus 0.3B plus 0.6C. So it's a sum over the possible values times the probability of getting that value. We also have the law of large numbers. So this law basically say that the average of proportions are likely to be more stable with more trials, while the sums or the counts are likely to be more variable. This does not happen by compensation of a bad run of luck, because independent trials have no memory. And to understand this better, I would highly recommend looking at example 8.6 of section 8.3 in the online notes, because it explains very, very clear of what does it mean by this entire paragraph of the law of large numbers. We also have the last part is simulation method. So in reality, to determine these probability, there are multiple ways that you can use. You can either run different trials and you run it many times, and then the proportion or whatever mean that you have is getting closer and closer to the actual mean of the population or what of the distributions that you're looking for. Or you can follow this methodology saying first you have a probability model, and then you have a chance process that give you a number every single time. Then you have a computer randomly generate as many instances of this process until the pattern of interest appears. So kind of like you run a lot of trials and trying to get closer and closer to the actual values that you're looking for. And depending on how many variables and also how good you are as designing the process, you can have better control on the process and see how many times you need it to be repeated. So say if you start a process and like throw them many times, like doing different trials, if you have good technique and you make sure that the control is the same every single time, and so the technique is standard, then you don't need as many repetition as you just blindly follow the procedure and do not actually pay much attention to the control. And then the last part is the kind of like related to the practice problem is the concept of mutual exclusiveness. So two events are mutually exclusive if they cannot occur at the same time. So say things like you can have three possible outcome of an event. So say if you do that event and you have three possible outcomes as A, B, and C, of course your outcome cannot be A and B at the same time. It can only be either one of them, but not both at the same time. So that's called mutually exclusive. And this concept should be noted to be different from independent. So independent is between different trials. Then if you do trial 1 and do trial 2, they don't have anything to do with one another. But then mutually exclusive is usually about one single trial, and you're talking about different outcomes possible in that trial. To understand that better, I would highly recommend trying out practice questions and problems. And so in this case, the first one, again, as I always say, mute me if you want to work on it on your own, or we can work on it together. Customer at a gas station pay with a credit card, a debit card, or cash. 70% don't pay with cash, and 20% use a debit card. So you have three different outcomes: credit card, debit card, and cash. So you have 70% don't pay with cash. So we only have three possible outcomes. So the sum of these two is 70%. And 20% use debit card. Now the total of these is 100%. Therefore, we have 30% using cash and 50% using credit card. Now let's see what the question is asking. What's the possibility that a random selected customer pay with cash? Now, as I said, this is one of a very good procedure that you guys should write down. So whenever you're given something about probability, try to list out all of the possible outcomes and what you already know about that probability or what the statement already given. Try to use all the values given and derive the probability of each individual outcomes. Then look at the questions, because if you look at the questions too early, sometimes it doesn't really give you an idea of like exactly what you have to do. But if you do this thing first and then you look at the question, usually you're gonna get the immediate answer. And also it helps you to get like a better understanding and get a big pictures of your problems. So what a possibility at a randomly selected customer pay with cash? As we see here, cash has a 30% of the customer, so the answer is C. Now let's see the next questions. What is the probability at a randomly selected customer pays with a credit card? And now with this diagram in mind, and we already derived everything at the beginning from the given information, we can immediately come up with the answer, which is also C, 0.5. Now, as I always say, if you have any questions about the step that I was doing or like the logic behind whatever I'm reasoning, please email me and let me know. I will be more than happy to answer your questions. Now let's go to the second questions. Again, mute me if you want to work on your own. When you flip a thumbtack into the air, it can land point up or point down. Since there are just two possibilities, the chance of each one must be 50%. Is it true or false? Now, in this case, I would say it is false because what happened is that it is true everything until this point. If you want to conclude that the chance of each one is 50%, you need one extra statement saying the possibility of each outcome is the same. You need this to have this statement to be true. Why? So you have the probability of A plus the possibility of B is equal to 1. That's whatever is given because there are only two possibilities. But they don't tell anything about the comparison between PA and PB. Therefore, there's no way you can conclude that they have the same possibility and each of them have 50% chance of happening. So this statement is wrong because the problem statement doesn't say that you need the same, each outcome have the same probability of happening. So in this question, the statement is wrong. The third one, when a sheep astragalus. So if you want to know what the sheep astragalus is, please look at the online notes. It's just like an old way in, in the ancient time where they haven't get the dice. They use sheep astragalus to kind of like throw a roll and try to get a number. So when a sheep astragalus is rolled, it comes up 1 10% of the time, then 3 40% of the time, 4 40% of the time, and 6 10% of the time. What is the expected value of the number that will come up in the next toss of an astragalus? Now what happened is that you roll an astragalus and it comes up with 1 over 10%, and then 6 later, so it's 7 times, and then 40% with also 7 times, 3 and 4. Therefore, you have your expected value as the value is 10% multiply 7 times of happening plus 40% of 7 multiply 7. So it's going to give us 3.5. And so that is the weighted average, which is also, this is the value. This is, oh, sorry. Hang on. I think I make a mistake here. So when you roll a sheep astragalus, there are 4 possible outcomes. You have 1, 3, 4, and 6. This one happens 10% of time, 40, 40, and then 6 is 10. So the expected value is going to be, this is the value, and this is the probability. Then we have 1 multiply 10%, plus 3 multiply 40%, plus 4 multiply 40%, and 6 multiply 10%. And so this is the value multiplied its possibility, and you sum all of those together. You're going to have 0.1 plus 1.2 plus 1.6 plus 0.6, which is going to give us 3.5, which is C. And so this is just following the definition and the basic way of computing the expected value. The next one, question 4, again, mute me if you want to work on it on your own. A college student is taking a multiple choice test that have 20 questions. Each question has 4 possible answers. We would like to simulate what will happen if the student guesses randomly on each question. So the key here is randomly, which means that each answer has the same chances of being chosen. And so specifically, we would like to examine the number of correct answers. Which of the following methods is appropriate to simulate this situation? So the thing with simulation is that the probability model that you're choosing should have the same kind of like possibility for the same answer. So say instead of choosing answer, you might do something else that also have 4 possible choices, and each of the choices have the same chance of being chosen. So let's look at the answer choices. A, repeatedly flip a fair coin 20 times, keeping track of a number of heads. Now A is not okay because it only have 2 possible outcomes. It's either going head or tails. So the fair coin is the term given to say that the chance of each side of the coin is the same. If you have an unfair coin, one side of the chance have higher possibility to happen to get. Therefore, A is not suitable because they only have two possible outcomes. We need some simulation that have the same four possible outcomes and each of them have the same chance of happening. Now let's look at B. Repeated a random number generator to generate 20 random numbers between 1 and 4. Count the number of 4. Now look at B and consider the number of outcomes. B is suitable, but let's see the rest. C. Repeatedly roll a 6-sided die and count the number of 4. Now with C, the problem is that you now have 6 possible outcomes and it wouldn't work because it doesn't follow kind of like the similar number of outcomes and it's not a very good method of simulation. So C is also not right. Therefore, D is also not right. B can possibly be right if you do it the right way. So what we do is that when you repeatedly you choose a random number generator to generate a number between 1 and 4 and do it 20 times, it follows what we need for the number of outcomes. And you count the number of 4s. Now, someone might say, okay, your answer doesn't have to be 4. Well, I mean, the thing with this is that you don't need to count. You can count the number of 1s. You can count the number of 3s. It doesn't really matter as long as you make sure, because every single answer, every question have one single answer, and it had 25% to be chosen. So by just counting the chance of getting one value, you basically follow the same thing because every time you create a new number, you have 25% of choosing 4 as well, right? So it doesn't really matter what number you count. You can count a number of 1s, you can count a number of 2. The thing that really matters is that every choice only have 25% of happening. This is similar to the questions where you have 25% of choosing the right answer. Do you understand what I'm saying? Okay, let's go to the next questions. Again, if you want to work on it, mute me. Which of the following best describes independent events? A. Whether the next customer at a gas station is wearing a coat, and whether the last customer at a gas station is wearing a coat. Now B. Whether the next customer and the last customer are pays with a credit card. Now, the answer is A here. Let's think about it. When you do B, right? There is no, it doesn't say anything else about like the bank that the customers are using. So if you just say like in any kind of situation, the fact that the first customer used credit card and the last customer using credit card has very little to do with one another unless they were using the same bank with the same discount and all kind of that stuff, but it's not very likely to happen at the same time with customer not really knowing one another. Now let's think about A. When the customer is wearing a coat or not might have something to do with the weather, and the weather is applicable to everyone. So it doesn't need to have a lot of coincidence happen to get both customer wearing a coat, because it has something to do with the weather, which applies to everyone, and it doesn't have to be a specific weather to wear a coat. It can be really hot and they were wearing a UV proof coat, or they can be in the winter where they have to wear like a waterproof and windproof coat for the snow and all kind of that. Therefore, A is more likely to be independent events than B, where you need a lot of other factors and a lot of coincidence to make it happen. So the answer is A, and it comes, these kind of questions relate a lot to reality. So I mean, this is a very good practice, and you should actually understand like the underlying behavior, the underlying mechanism of these questions. Now it comes to question 6. Which of the following are mutually exclusive events? A. Getting a head on the first toss and a tails on the second toss. Now, as I say, mutually exclusive usually have things to do with different outcomes of the same trial. So thinking about A, it's more like independent events than mutually exclusive. And if you think about it, you can only get head on the first toss and also tails on the second toss. It doesn't have anything to do with one another, and both of them can happen in one of your samples. So A is not A is not the choice for mutually exclusive events. Now B, a randomly selected household having a pet dog and the same household having a pet cat. Again, this can always happen. We usually think that, okay, if you have a dog and a cat in a house, they will fight, but there's no rule and there's nothing to prohibit a person getting a dog and a cat together at the same time in the same house. So B is also not correct. C, raining in Philadelphia on March 1 and raining in New York on March 2. This again can always happen because, you know, both of them, you can have rains at this place and rain in the other place at the same time, not to mention like happen at on different dates. So this is possible. So C again is not correct. Now the answer is D, and let's see what it is. Obtaining both a 3 and a 4 on the same row of a die. Well, I mean, when you roll a die, you can only get one number at a time, and that's like the general law of physics, where you cannot have a row just standing between two numbers, and that is not like a stable balance for a row. Consider its weight distribution. So you can only have one number for each throw of a die. So obtaining both a 3 and a 4 in the same row is not possible to happen at the same time. So it's called mutually exclusive events. Now the last one, again, mute me if you want to work on it on your own. The median household income in the state of Pennsylvania is about $52,000, which is more likely. A, the chance that you get between 45% and 55% of the household having an income over 52 is greater with a random sample of 100. So greater with a sample of 100 than for a sample of 300 or 500. And then B is just smaller. And then C, the chance you get between that is the same whether you take a random sample of 100 or a sample of 500. So let's think about it using the law of large numbers. So when you have the median income, which means it's 50% of, it's the 50th percentile. So if you have a bigger trial, like a bigger sample, there's more likely that you're gonna obtain that proportion. So if you look again at the law of large numbers, average and proportion is more likely to be stable with a larger sample. So therefore, the median, this value of median, $52,000, is more likely to hold with a larger trials and a larger samples. Therefore, we're gonna have the chance of getting an income over 52,000 is going to be, so the chance of having the 52,000 less than, it's not a median, so it can be small, it can be like 40th percentile and all of that. Then so again, can I say the chance of 52,000 not being the median, so the chance that you get between this is smaller with a smaller sample and larger with a larger sample. Therefore, the answer is B. That means that you're gonna get 52,000 as there's a higher chance that 52,000 is the 50th percentile if you have a larger sample than a smaller sample. That is based on the law of large number, when average and proportion is more likely to be stable with a larger sample. So B is the answer. And this one I would say is the most challenging practice questions. And if you have any questions with this, please feel free to let me know, or like, you know, practice and like maybe re-listen to my answer to kind of like understand it a little better. It's up to you. Well, if you don't have any other questions, I'll end the sessions here, and the next review is gonna be next Thursday at the same time. And I would recommend trying the practice problems again. So have a great weekend, guys, and I'll see you guys next week. Thank you.